Hello, this is Adolfo Gonzales. I'm the product manager for the engineering desktop tubular applications, and I'm going to give you an update on the what is new on the EDT 5015.1 release. So let's start with history of the work that has been done in the past approximately 12 months. So um, in 2017, October 2017, we did the release of the EDT 5015, and it includes enhancements on the tubular application, specifically for Wellcat limit state formulas, and for Wellcat and StressCheck, updates on the design limit plot such that it support the latest changes on the API collapse equations. We also did work on the CasingWear applications, and one of the enhancements was associated with wear factors modeling tool. In March of this year, 2018, we addressed a performance issue in StressCheck as part of the hotfix CDT 5014.1.7. Now, in April 2018, we are adding additional new features to both Wellcat and StressCheck, as you can see. We have plans moving forward to the end of 2018 to support well inclinations about 90 degrees for Wellcat and few other enhancements as you can relate and see. And finally, this, as always, there's a list of new features that we are contemplating and evaluating at this time for future releases. So let's take a look at the Wellcat enhancements with more details. For Wellcat, essentially version 5015.1, we have implemented separate representation of the pi body design limit and the ISO service load limits plots. Also, we add to the summary results of loads the buckling regime status. And finally, we add a new load for Wellcat, name it above below packer load. This is a classic StressCheck load that has been now is supported in Wellcat. Details about the pi body design limit plot is configuration can be found in a SPE paper 189670 for more details. Also, it's important to highlight, and we have addressed a defect specifically associated with well configurations with the tubing string set shallower than well TD, such that the string of interest, the casing or line string of interest, has the proper internal pressure representation. So let's take a look at the demo. In reference to the design limit plot for the pi body and the ISO connections. So with the 5000.15.1, now we can have independent representation of this design limit plot for the pi body and the ISO connection. Well, let's take a look. On the right hand, we have the ISO service load limits, the new representation. The workflow to bring in the envelope hasn't changed. So just right click, select ISO service load test data, assuming that you already have specified a ISO connection values in the corresponding library. We import it, and once we import it, we enable that in the plot as you can see. With this, now we can have accurate definition and representation of the loads based on differential pressure and equivalent axial load for the pi body, and the load points based on differential pressure and axial load for the ISO connection envelope. Another enhancement to the application is the addition of the buckling regime to the casing load summary results. So with this, now we know just basically report dog leg values for the particular loads and the required pickup force to prevent buckling, but also now details of the buckling regime along the pipe uh, with a status such as non-helical or sinusoidal buckling, which is going to change depending on the load scenario, as you can see at this time. Finally, we have created a new load scenario in Wellcat that represents the above-below packet scenario typically used in a StressCheck. So this load scenario can be selected as you can see this time for the load definition, and corresponding details can be specified with a specific definition for the packet depth, as well as perforation depth, pore pressure, perforation depth, density above packet, density below the packet, and the packet failure option as defined in a StressCheck. So let's take a look at the impact of simulating, for example, a failure on the packet sealing conditions that put in contact basically a hydrostatic of a 10 ppg completion fluid about the packet and 2 ppg representing the reservoir fluid gradient, pressure gradient. So let's apply that and recalculate. Now you can see now how the internal pressure profile represents a drop in the completion fluid column due to the failure on the sealing condition of the packet, putting in contact a heavy fluid like 10 ppg, as I mentioned, with the 2 ppg fluid below the packet. The new enhancement for the stretch applications are the following. We have create an option for the calculations associated with the loss return with mat drop load case. And this option is associated with the definition or identification of the worst case scenario, not just based on the maximum or worst mat drop length, but the the lowest safety factor condition. And also we have implemented a scenario of negative pressure test, typically used in offshore deepwater wells. For the low return with mat drop, in a scenario similar to the ones that you see here, a taper well mechanic configuration, it's possible to experience for the string of interest changes on the internal pressure profile such that not necessarily the worst mat drop represent the worst case in terms of safety factors. We also have resolved in this release scenarios associated to gas over mud, specifically for casing liner configurations, where until now incorrect internal pressure profiles were reported. Now, for those type of scenarios, we extrapolate the pressure that is calculated at the top of the liner to the surface pressure point calculated um, for the internal pressure maximum anticipated internal pressure profile. Let's take a look at the demo of the new functionality. Let's take a look at the long return with mat drop scenario. This is a similar configuration of taper designs that we were referring to just before. So you can see for the string of interest that we have a collapse safety factor equals to 8.41. Let's take a look at the collapse load definition, and the one that has been defined is the log return with mat drop. This log return with mat drop for the input conditions report for the maximum mat drop of 659.3 feet, a collapse safety factor of 8.41. Alternatively, now the user can go and activate the solution taking into consideration the lowest safety factor. So let's click the option and then apply. And you will notice now that the mat drop level for the worst case based on safety factor is less than the maximum mat drop on the previous calculation. However, these results, even though it doesn't have the maximum mat drop, have a much lower collapse safety factor. So the user now can look into either what is the worst condition based on mat drop or what is the worst condition based on safety factor, specifically for well configurations of the taper design, as I mentioned earlier. User can basically go back and forth between the two calculations by resetting the initial settings for the low case and to generate the previous collapse results. The new addition to a StressCheck is a negative pressure collapse low case. So the user can select the negative pressure test, which allows the user to set a live fluid mat interface depth column, which for offshore wells default to the mud line, and the live fluid definition as well as the mat weight for the annulus of interest. So currently with these inputs, what you see here is essentially a corresponding match between the internal pressure and external pressure all the way to a point of reference which is 12,500 feet. This represents the top of cement as you see in the schematic. Now we are going to force essentially the default value for the live fluid that for subsea wells is equivalent to 8.6. Now we apply it and automatically you can see the impact of much lower pressure profile internally compared to the initial state that was mentioned. So very quickly we can define this low case and is as part of the design methodology for your well for collapse loads. All right, so these are the new enhancements and hopefully you can bring it to your as part of your design methodologies in the near future.